This is a video from the Exam 2 Review Part 1 in my linear algebra. Let's take a look at problem 3. Let V be the set of all column vectors u1, v1 that belong to R2 where v1 is greater than 0. And we're going to define vector addition and scalar multiplication as follows. If I take the column vector u1, v1 and add it to the column vector u2, v2, I'm going to add the first components and then multiply the second components. So in other words, u1, v1 plus u2, v2 is equal to u1 plus u2, v1 times v2. So the column vector, again, u1, v1 plus the column vector u2, v2 is equal to the column vector u1 plus u2, v1 times v2. And when we look at scalar multiplication, we're going to take k times the column vector u1, v1, and that's going to equal ku1, v1 to the k. And we want to show V is a vector space with those given operations. The column vector 0, 1 belongs to R2, and notice how the second component is greater than 0. So in other words, notice how 1 is positive. So the column vector 0, 1 belongs to V, and we can thus say V is non-empty. Okay, now here's how we're going to start this. Let column vectors u1, v1, u2, v2, and u3, v3 belong to V, and k and m be scalars. Okay, since the column vectors u1, v1, u2, v2, and u3, v3 belong to V, we can say that those second components are positive. So in other words, we can say v1, v2, and v3 are all positive. We want to show that V is closed under scalar multiplication. So we want to show the column vector u1, v1 plus the column vector u2, v2 belongs to V. But notice, if I take column vector u1, v1 plus column vector u2, v2, this is equal to the column vector u1 plus u2, v1 times v2, right? Remember, we add the first components, multiply the second. Now notice, this column vector belongs to R2, and v1 times v2 is positive. Why is it positive? Because v1 is positive and v2 is positive. When you multiply two positive numbers together, their product is positive. So we can say that the column vector u1 plus u2, v1, v2 belongs to V. And so therefore, the column vector u1, v1 plus the column vector u2, v2 also belongs to V. And we can thus say V is closed under addition. So axiom 1 is satisfied. Now we're going to show that column vector u1, v1 plus column vector u2, v2 is the same as column vector u2, v2 plus the column vector u1, v1. So we're going to start with the left side. So let's take column vector u1, v1 plus column vector u2, v2. But we have to watch how vector addition is defined in this problem. We're going to add the first components, multiply the second. So over here we get column vector u1 plus u2, v1 times v2. This, to me, from this step to this step, is crucial. Real numbers are commutative under addition and multiplication. So we can write this as column vector u2 plus u1, v2 times v1. But this is equal to column vector u2, v2 plus column vector u1, v1. And we have thus shown that these vectors commute. So in other words, we have shown column vector u1, v1 plus column vector u2, v2 is the same as column vector u2, v2 plus column vector u1, v1. Now we're going to show the associative property. So what we're going to do is take column vector u1, v1 and add it to the quantity, this quantity. So in other words, in parentheses, we have column vector u2, v2 plus column vector u3, v3. Now, we got to take care of the parentheses first. So in the second line here, we get column vector u1, v1 plus column vector u2 plus u3, v2, v3. Now, adding again, this is equal to the column vector u1 plus, in parentheses, u2 plus u3, v1 times the quantity v2, v3, right here. Now, this is the key step. Remember, real numbers are associative under addition, and they're associative under multiplication. So this is crucial right here. You have to show that. So this is equal to the column vector. Notice how u1 plus u2 is in parentheses, and then I add u3. That's the first component. And in the second component, notice how v1, v2 is in parentheses, and then I multiply by v3. And then I can begin to unwind. So this is column vector u1 plus u2, v1, v2, plus column vector u3, v3. Now, in parentheses, we get column vector u1, v1, plus column vector u2, v2, and then I add u3, v3. And we have thus shown that the associative property works. So notice it at the end, if I take the column vector u1, v1, and I add in parentheses column vector u2, v2, plus column vector u3, v3, we get this is equal to, in parentheses, u1, v1 plus u2, v2, and then on the outside of the parentheses, we're adding u3, v3. So the associative property under addition works. Now, we established in the beginning that 0, 1 is going to be, that's going to serve as the zero vector for v. Okay? And I've already established that 0, 1 belongs to v by showing v is not empty. And I want you to notice, if I take column vector u1, v1 and add it to the column vector 0, 1, we get column vector u1 plus 0, v1 times 1, which is equal to u1, v1, that column vector. And then if I take the column vector 0, 1 and add it to a vector in v, right, I get that same vector back. So it works the other way too. And so 0, 1 is that zero vector. Number 5. We're going to show additive inverses. But additive inverses may not look like what you think. So we're given that column vector u1, v1 belongs to v. Now, notice in the first component we're adding. In the second component we're multiplying. So I want the additive inverse of the first component. And that's why I looked at negative u1. And then I want the multiplicative inverse of the second component. And that's why I looked at 1 over v1. And so notice, given column vector u1, v1 that belongs to v, the column vector negative u1, 1 over v1 also belongs to v, since this column vector is in R2, and if I look at the second component, that's positive, right? Now, if I take this vector and add it to u1, v1, I want you to notice what we get. So, take the column vector u1, v1 and add it to the column vector negative u1, 1 over v1. So I want to make sure you guys understand. In the first component, I'm adding, and that's why I looked at the additive inverse of u1. In the second component, we're multiplying, which is why I looked at the multiplicative inverse of v1 to construct my additive inverse, basically. So when we add these, take the column vector u1, v1 plus negative u1, 1 over v1. This is equal to u1 plus negative u1, v1 times 1 over v1. And this is equal to the column vector 0, 1. And very similarly, if I take negative u1, 1 over v1, and add it to u1, v1, that column vector, I get negative u1 plus u1, and this is a column vector. The column vector negative u1 plus u1, 1 over v1 times v1. And this is also equal to 0, 1. And so, how do I say it? There's a negative. So given any vector in V, we can find the negative of that vector that is also in V. Now, this is dealing with scalar multiplication. So if I take k times the column vector u1, v1, this is equal to ku1, the column vector ku1, v1 to the k. That column vector belongs to R2, and the second component is positive. Do we understand why this component is positive? The reason why that component is positive is because we already know that V1 is positive. So when I take V1 to any power, that will always be positive. And so we can say that k times the column vector u1, v1 belongs to V, and therefore we can say V is closed under scalar multiplication. Number 7, I'm going to take k plus m times the column vector u1, v1. So we have to really understand how scalar multiplication is defined. So I'm going to take k plus m and multiply it by the first component, and then take v1 and raise it to k plus m for the second component. So look at this line here. So we get the column vector k plus m times u1, v1 raised to the k plus m. But we have the distributive property for real numbers. So in other words, I'm going to take ku1 plus mu1 to get this first component, and then to get the second component, I take v1 to the k times v1 to the m. That is legal. Now, I can break that apart. So in other words, k plus m times the column vector u1, v1 is ku1, this column vector. So let's reset. Take k plus m times the column vector u1, v1. This is the column vector ku1, v1 to the k, plus the column vector mu1, v1 to the m. But this is k times the column vector u1, v1, plus m times the column vector u1, v1. And we've proven axiom 7. Axiom 8. Take k times the quantity, and in parentheses we get column vector u1, v1 plus column vector u2, v2. But this is k times the column vector u1 plus u2, v1, v2, which is the column vector k times u1 plus u2, v1, v2 to the k. And remember, we have the distributive property, and we have properties of exponents, right? We have all those things. So we can write this as the column vector ku1 plus ku2, v1 to the k, v2 to the k. And this is the column vector ku1, v1 to the k, plus the column vector ku2, v2 to the k. But this is equal to k times the column vector u1, v1, plus k times the column vector u2, v2. And thus we have shown that k times, in parentheses, the column vector u1, v1, plus column vector u2, v2, is k times the column vector u1, v1, plus k times the column vector u2, v2. So we've shown that. Number 9. So if I take k times the quantity, or k, and then in parentheses, I have m times the column vector u1, v1. This is equal to k times the column vector mu1, v1 to the m, which is k times mu1, and then I have v1 to the m all raised to the k. Now remember, real numbers are associative under multiplication, and we still have those properties of exponents. Remember, v1 is positive, so all good things happen, right? And so this is a key, right, to go from here to here. We need to be able to do that and establish that. So on the last line, notice how I take km and multiply it by u1 to get the first component of that vector. And then the second component is v1 raised to the mk. Okay, that's important. And this is the column vector km u1, v1 to the km. And so all I did was say mk is the same as km. That's all. That's how I get to this. And then I can pull that km out in front and say that this is km times the column vector u1, v1. And so k times, and then in parentheses, m times the column vector u1, v1 is km times the column vector u1, v1. Last axiom. 1 times the column vector u1, v1 is equal to 1u1, v1 to the first, which is the column vector u1, v1. And so therefore 1 times the column vector u1, v1 is the same as the column vector u1, v1. Since V satisfies all 10 axioms, we can say V is a vector space. And the one thing you need to establish from the beginning is that zero vector, because that shows V is non-empty. But you want to show V is non-empty by getting the zero vector. Why? Because that helps me get additive inverses. So in other words, when I go for axiom, I believe it's 5. When I went for axiom 5, it's helpful to know the zero vectors in there. So, okay, that'll do it for this video for the exam 2 review. And this was part 1, by the way. This was part 1, and this was problem 3. Okay, thank you.